Today we discuss on MCQ 2021 paper DSE B2.3 Advanced Mechanics. First question is, answer the following multiple choice question. A constant of the form f vector rj vector comma t equal to 0 and j equal to 1 comma 2 comma n is called a bilateral constant and also geometric constant. A finite and geometric constant is free from Rj dot vector and can be written in the form if Rj vector comma t equal to 0. And if it does not contain the time t explicitly, that is del f del t equal to 0, then the constant is called stationary. Otherwise, it is non-stationary. Obviously, here if Rj vector comma t does not contain Rj dot vector, so it is a geometric constant. A kinematical or differential constant involves with Rj dot as well as and is of the form if Rj vector comma Rj dot vector comma t equal to 0. When constants are in the form of equalities, then it is called bilateral constant. So here we get two correct options, 2 and 4, bilateral constant and geometric constant. Next question, 1b. The number of degrees of freedom of a rigid body is 6. A rigid body is a system with a large number of particles with point masses not all lying on one line and with all its particles at fixed distances from each other. Take any 3 points which are not collinear, that is 3 points masses connected by 3 rigid massless rods, then this system consists 3 particles, so capital N equal to 3 and 3 constraints k equal to 3, which are x2 minus x1 square plus y2 minus y1 whole square plus z2 minus z1 whole square equals to L1 square, and so on, x2 minus x3 whole square and dot 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 equal to L3 square, and x3 minus x1 whole square plus dot 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 L2 square. So first constraint equalities gives the first particle and second particle distance square, and second equality gives second and third particle distance, and third equality gives third and first particle distance square, where Li are the lengths of the connecting rods and the points x1, y1, z1, x2, y2, z2, x3, y3, z3 are the coordinates of the 3 particles. Hence, the number of degrees of freedom by formula 3n minus k. So here 3 particles, 3 into 3, and number of constants k, so minus 3. So you get 6. If one fixes these 3 points, the body consists of n particles is immovable. Hence, the number of degrees of freedom of a rigid body having n greater than equal to 3 is 6, which is independent of n. So here the number of degrees of freedom of a rigid body is 6. Next question C. If the Hamiltonian of a one-dimensional dynamical system is given by H equal to half of this and alpha, beta, gamma constants, then Poisson bracket P comma H is equal to correct option is 4 minus beta Q minus gamma P. So this Hamiltonian is given by this, and here Poisson bracket of P and capital H is given by the relation 4. Here the Poisson bracket P and H equals to del P del Q del H del P minus del P del P del H del Q. And this del H del P this equals to 0 because del P del Q equal to 0. So because P is the generalized momenta, so M into Q dot. So obviously del P del Q equal to 0 because Q does not appear in the generalized momenta P. So this term 0, this product term 0, and this del P 1 and del H del Q. So this equals to minus del Q of H, and already H, capital H is given by this half of alpha P square plus beta Q square plus 2 gamma PQ. So after partial differentiating with respect to Q, we get this minus beta Q minus gamma P. Next question B. Two weightless inextensible rods AB and BC are suspended at A and jointed by a flexible joint at B. The degrees of freedom of the system is 4. Here A is the point, say coordinates with 0, 0, 0 origin, and B is the point x1, y1, z1, and C is the point x2, y2, z2. And length between A and B, AB, length of AB is L1 and length of AB, BC is L2. Assume B and C are two particles and the constants are fixed length L1 and L2. And we take in A as origin and B and C, so we get two equalities. First is x1 square, x2, x1 square, y1 square, z1 square equal to L1 square from the distance AB, and from the distance BC we get x2 minus x1 whole square and plus dot 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 equal to L2 square. Hence, the number of degrees of freedom is equal to 3 into number of particles minus number of constants. Here, number of particles 2, so 3 into 2 minus number of constants is 2, and because this and this, so 4 is the degrees of freedom here. Question E. The Lagrangian of a free particle of mass small m and velocity small v is given by L equal to mv square by 2. Correct option is this. In an inertial frame, a free particle will move with constant velocity, both direction and magnitude. The uniformity of space means there is no preferred direction of the velocity. So the Lagrangian capital L can depend on the magnitude or square of the velocities. That is L equal to L v square. Also, we know L is equal to T minus G. T is the kinetic energy and V is the potential energy. So this equals to half mv square, and because here potential energy is 0, free particle of mass m and velocity v. So free particle is half mv square is the kinetic energy only here, and no potential here, energy here. So L equals to half mv square is the Lagrangian of this system. Next question, if the Hamiltonian of a particle of mass m is H, capital H equal to this, and where Q is generalized coordinate and P is corresponding momentum, the Lagrangian of the particle is question correct option is 2, m by 2 q dot minus q air whole square. Here, Hamiltonian capital H equal to p square by twice m plus p into q. Also, you know that p dot, that is dp dt, this equals to minus del h del q equals to minus p, and partiality with respect to q from 1 we get minus p, and q dot, that is dq dt, that is equals to del h del p, and also del h del p from 1 we get twice p by twice n equal to this. So we get p equals to m q dot minus q whole into m, this. Also, we know that Lagrangian L equal to pq dot minus h, capital H. So pq dot minus hello capital H from 1, we put this, and we simplification, we get m by 2 q dot minus q whole square. Next question G. Consider the Hamiltonian H and the Lagrangian L for a free particle of mass m and velocity v. Then question G, option 3, H and L are equal. H and L are equal. Here Lagrangian L equal to T minus V. T is the kinetic energy, V is the potential energy, and Hamiltonian H equal to T plus V. For a free particle, obviously potential energy equal to 0, V equal to 0, then L equal to H equal to T, that is equal to half mv square, and both are quadratic in V. So Hamiltonian and Lagrangian for a free particle of mass m and velocity v, we get H equal to L. Next question H. If a symmetry is found to exist in dynamical problem, then there is a corresponding constant of motion. This is Noether theorem. A statement of Noether's theorem. If a system has a continuous symmetry property, then there are corresponding quantities whose values are conserved in time. So this is the statement gives the Noether's theorem. Next question I. Dynamical system having kinetic energy T and potential energy V is described by the Hamiltonian H. Assume that the equations defining the generalized coordinates do not depend on time T. Then correct option is 1, H equal to T plus V and is conserved. If the transformation to generalized coordinates is independent of time T and the potential energy is not velocity dependent, then the Hamiltonian is equal to the total mechanical energy. That is, capital H equal to T plus V equals to the total mechanical energy. Thus, the generalized energy Hamiltonian, capital H, equals to the total energy, capital E, if the constants are time independent and potential energy is velocity independent. Now, del L del T equal to minus del H del T. If del H del T equal to minus del L equal to 0, that is H is as well as L are not explicitly functions of time t, and if constants and coordinates transformation are time independent, then H is conserved, that is H is a constant of motion and H equal to E. And 2, option 2, this if constants and coordinate transformation are time dependent, then H is conserved but H not equal to E. And case B, if del H del T equal to minus del L del T not equal to 0, This implies H is not conserved. H is not a constant of motion. And then we get if const, constraint and coordinate transformation are time independent, that is H equal to E, and constraint and coordinates are time dependent, then H not equal to E. So we summarize these results, these constants and coordinate transformation when Hamiltonian H and del H del T equal to minus del H del T equal to 0, and this time independent, then we can say H is conserved and H equal to E, and time dependent, then Hamiltonian time dependent, then H is conserved and H not equal to E. And if del H del T equal to minus del H del T not equal to 0, then capital H is not conserved and then capital H equal to E. And when H is time dependent, then H is not conserved and H not equal to E. So here, dynamical system kinetic energy, potential energy, we describe the Hamiltonian. Assume the equations defining the generalized coordinate do not depend on time. So H equals to T plus V and H conserved, not depend on T, and independent, not Hamiltonian coordinates, generalized coordinates, and do not depend on time. T, then H is conserved. H is conserved and del H equal to H equal to T plus V equal to kinetic energy E, kinetic energy E, in this case. Last question J. A mechanical system is described by Hamiltonian H equal to this as a result of canonical transformation generated by F Q capital Q equal to minus capital Q by small q. The Hamiltonian in the few new coordinate capital Q and new moment of capital P becomes option 1, 2, 3, 4. Here, correct option is 4. Correct option is 4. Here, H is given by this, and F is the transformation minus capital Q by small q. So the first form of the generating function, this F1 small q capital Q, the equation of transformations are small p equal to del F by del Q equal to del Q of capital F equal to capital Q by small q. So we get capital Q by small q square, and capital P equal to minus del capital Q F, that is equal to plus 1 by q. So small p equal to capital Q by small q square equal to capital Q 1 by small q square, that is 1 by small q means capital P. So this capital Q capital P square, and capital P equal to 1 by q, that is small q is equal to 1 by capital P. Substituting for old coordinates small q and small p in terms of the new coordinates capital Q and capital P, we get Hamiltonian for the new coordinates as capital H. So we put here value of small p and small q by capital P and capital Q, and we get the result, this. Option 4. After simplification, we get the option 4. Thank you.